Hi guys, today we're going to be talking about the cubic function, which is when you have this equation y equals x cubed. We're going to first be looking at the features of the parent function, and then from there we're going to look at how to graph variations of this function using graphing transformations. But we have to start somewhere with our graphing transformations, and so the place we choose to start is with the parent. The parent function is when you are just looking at the simplest form of a cubic. The simplest form of a cubic is where you're just cubing x alone. So what I will do is I will take some x values, and I will take the x values that are centered around the origin. So I'll have a couple negative x values, the origin itself, and then a couple positive x values. And then I will plug those numbers in here to see how the y values behave, to see what they equal. So when I raise negative 2 to the third power, I get negative 8. When I raise negative 1 to the third power, I get negative 1, so on and so forth. So I am essentially just cubing x, right? The y values, which I have right here, are what I get after I take these x values that I have over here and raise them to the third power. So then when you put these points together, it gives us the shape of the parent graph, and then from there we can kind of see the characteristics of that parent graph. So I am going to plot these 5 ordered pairs over here. So I have 0, 0, which was the origin, which I centered my other points around. I have 1, 1, 2, 8. Just kidding, that's right here. And then negative 1, negative 1, and then negative 2, 8. And when I connect those points, I get a shape that looks like this. So I will probably in class refer to this as the squiggle shape, for lack of a better word. Like, I don't have a fancy math word for it, like quadratics, we called them parabolas. This, I'm just going to call it a squiggle. Maybe it could be like a stretchy S. I don't know. If you come up with a better a description of this shape, please share it with me so that we can use that better description in class. But basically, this is how a cubic function behaves, because with a cubic function, if you have a positive x value, so for all x's that are on the right side of the y-axis, these are positive x's, the resulting y values are going to be positive. So your graph is going to go up on the right. But then you go over here to the left, these x values to the left of the y-axis are all negative. And when you take a negative number and raise it to an odd power, like right here when I took negative 2 and cubed it, the result of that is negative. So instead of going left and up like what happened when we had the quadratic function because we were squaring the number, now when I go left on the x-axis, I'm going to go down on the y-axis, because when you cube a negative number, you get a negative. In other words, this time our range is going to include negative numbers. Okay, so now let's take a look at, so we talked about the range a little bit. Let's go ahead and write down some of these defining characteristics. So with the parent function, which again is just y equals x to the third, the domain would be anything that I am allowed to plug in for x. And basically I can plug in any real number for x, and then I can cube that number. So you can either write all real numbers, or you can write it like this, with the double stem r, or you can use that interval to show that basically all negative x's and all positive x's, all of these values along the x-axis, they all have corresponding y values on this curve, because every single one of them can be cubed. And then for the range, which we talked about over here, the range also can include all of these positive y values that go up the y-axis and all the negative y values that go down the y-axis. So the range is also all real numbers. Or you can put the little r with the double stem, or you can write the interval negative infinity to infinity. But basically what this is saying is that I can take any x value I want and I can cube it. And then what the range is saying is that you can cube any x you want and you can end up with any y value. So no x's or y's are left out. This is a very inclusive function, which is one of the things I really like about it. Okay, so the other thing I want us to notice about this particular function in comparison to the quadratic is that this function is one-to-one. In other words, this function passes the horizontal line test, and that means I could run a horizontal line through this curve at any point, and it would only intersect the curve once. What that means is that there's only one x for each y. Each of these horizontal lines that I run across the curve is representing a specific y value. Where it hits the curve is representing a specific x. So if it hits the curve only once, that means there's only one x for each y. And because this is already a function, there's also only one y for each x. So 1 to 1. It works both ways. One x for each y, one y for each x. Which is nice because our absolute value function was not 1-to-1, which meant the equations always had two, or often had two answers. Our quadratic functions were not 1-to-1, which again meant our equations often had two answers. But for these cubic functions, it is 1-to-1. So if given a y value and you're trying to go backward to find x, there's going to be one solution to that type of equation. Okay, so that's another key feature. It's 1-to-1. Then I want you to notice that this does not have a line of symmetry, but it does have a point of symmetry. So the origin, which is in the middle of this graph, if I were to rotate all points about the origin 180 degrees, they would map right back onto the other half of this function. So this function has what we call a rotational symmetry. If you rotate it 180 degrees, it rotates right back onto itself. And so that is a type of point symmetry. So this graph has a point of symmetry, not an axis of symmetry, a point of symmetry, because it's rotational symmetry, not a reflection. And for the parent function, that is at 0, 0, that middle point here. Eventually, when we do transformations, that is going to become our hk. But it's important for us to always keep in mind that for the parent function, a is 1, h is 0, and k is 0. So the origin for the parent function is also hk for the parent function, which in this case is a point of symmetry. So that hk will be your point of symmetry for all your transformed graphs as well. Let's see what else. So the x-intercept and the y-intercept, those are both at 0, 0, which has been the case for all of our parent functions. This function has no max and no min because it never changed direction. It always went in one direction the entire time. So the parent function only ever increases, and it increases across the entire x-axis. So in other words, because remember, for increasing and decreasing, we always read our graphs from left to right. So in this case, let's see, I'll use orange. As I run from left to right across the x-axis, as I'm going in that direction, all affiliated y values for those x's are moving up the entire time. So this is the left x, this is the right x. So this is saying from the left end of the x-axis to the right end of the x-axis, the y values are going up. They're increasing that entire time. Let's see, did I leave anything out? I don't think so. Oh, yeah, rate of change. So like the quadratic, this function does not have a consistent rate of change because the rates of change are different between most points. For example, if I look at the rate of change between these 2 points, 0, 0, and 1, 1, the rate of change there would be 1. But then if I were to go to the next 2 points, which was 1, 1 and 2, 8, my rate of change there would be 7. And then so on and so forth. So I have all these varying rates of change. So again, your rates of change for the cubic function basically vary. And so there is no one set rate of change. So that is giving us a pretty full picture for our parent function. Now what we're going to do is take this parent function and transform it. We're going to take these as our starting x and y's, which form the shape of this cubic, and then we're going to transform those using AHK transformations. Okay, so now we want to take our cubic parent function. Whoops, I made that quadratic. This should be cubic. And I want to graph transformations of it using A, H, and K. So in this AHK form, I have an A value of 1/2. I have an H value of -3 and a K value of -5. And as I'm writing this, I just realized I forgot to show you the generic AHK form for a cubic. It pretty much looks like AHK for all of the other functions, but instead of having a parentheses squared around the x minus h, it has a parentheses cubed. And that is what tells us that this is a transformed cubic function as opposed to a transformed quadratic. And so you'll notice the h is still opposite sign here. It always is for all of our different functions. And the AH and K do the same transformations to the cubic that they did with the quadratic, that they did with the absolute value, and that they do with any generic function. So like, for example, this 1/2, since it's less than 1, that's going to cause a vertical compression. So this squiggly graph should look a little bit more compressed than the parent one did. The h value of -3 is going to shift our graph to the left 3 units. And the k value of -5 is going to shift our cubic graph down 5 units. Okay, so to get the points to help us carry out the vertical compression and the shifting, I'm going to start with our parent points from the parent graph. So I'm going to start with the ones that were centered around the origin where I was just cubing x. I'm going to start there. So this is the parent x values and the parent y values. Then what I'm going to do is transform those points by multiplying a to the y values, adding k to the y values, or in this case subtracting 5, and then adding h, which is negative, to the x coordinates. So I take these -2, -1, 0, 1, 2, I subtract 3 from each of them. And that helps me shift all of these points to the left 3. Then I take all of these y values. So the -8, the -1, the 0, 1, 8, which this is what I got after I cubed x. So this is taking care of the cubing part, right? I take all of those numbers and I half them. So I get half of -8, that's -4. Half of -1 is -1/2, and so on and so forth. Then I subtract 5. So I do the vertical compression before I do the vertical shift. So then this one moves down to -9, this one moves down to -5.5, and so on and so forth. So then my new ordered pairs would be my shifted x's and my shifted y's. And notice the middle point should always correspond with your h and k, because it should be the point of symmetry for your graph. And then the other points should be centered around that. Okay, so I'm going to plot the point -5, -9, -4, -5.5, -3, -5, -2, -4.5, and then -1, -1. And so I get that squiggly shape, but the squiggly shape is just somewhat compressed when compared to the parent. It also shifted to the left 3 and down 5. So now my point of symmetry is now down at -3, -5, because that'll be based off of H and K. My domain is all real numbers. My range is all real numbers. Since I have a positive A value for this one, that means there was no vertical reflection. This graph is still increasing over the entire x-axis. So the increasing interval stretches from -infinity to +infinity. For the y-intercept, I can do what I've been doing, and that's just plug in 0 for x in the equation. And I just was using this equation up here and just plugging 0 right in there for x, following order of operations. Sorry, this is cubed. Keep forgetting that's cubed. So I get 3 to the 3rd, which would be 27. And then I have to take half of 27, which would be 13.5, and then I subtract 5, which would be 8.5. So my y-intercept for this graph would be at 0, 8.5, which if I look at my graph here, it's going up pretty quickly, so it makes sense to me that it's going to have to go all the way up to 8.5 on the y-axis before it actually crosses the y-axis. So I'm going to lock that answer in because it's corresponding to my graph. For the x-intercept, we're going to do something really similar to what we did with quadratics. So we do have to plug 0 in for y to start, because that's what makes an x-intercept an x-intercept, is if the y value is 0. And then we're going to isolate the cube. Just like when we did this with quadratics, we wanted to isolate the square. Whoops, this would be a 5 because 0 plus 5 is 5. Okay, so I added the 5 over, and now I'm going to multiply by 2 to both sides to get rid of the 1/2. That's a multiplication symbol there. It looks like a weird other thing. That was 2 times. Okay, and then I'm left with my cube. So just like with quadratics, we had a square here, so we square rooted. Now we have a cube here, so we're going to cube root. Cube root is like a square root symbol with a little index of 3, and we're just going to leave our answer this way. Notice I did not do a plus or minus here, because if, like, let's see, how do I say this? Because x plus 3 cubed equaled +10, that must mean that the original x plus 3 was already positive. You can't cube a negative and have it turn positive. That's only true when you square a negative, but not when you cube a negative. So if your something cubed is equal a positive value, then the original thing, whatever it was before you cubed it, would also equal a positive value. So it's not plus or minus, it's just plus. And then I just subtract the 3 to isolate x. So it's the cube root of 10 minus 3, which would be some irrational number, some decimal that we could plug in our calculator. And it would be somewhere right here. So it's going to be negative because 3 is bigger than the cube root of 10, right? And I'm subtracting 3, so that makes sense. This should be a negative number. Okay, so that was one example of sketching the graph using transformations and then going through and listing all of those defining characteristics. Oh yeah, I forgot to mention this doesn't have a max or a min. No max, no min. No constant rate of change, it's cubic. It only ever increases across the whole x-axis, and then these are how you find your intercepts. Okay, so let's just take a look at one more graph. I wanted to do one graph that has a vertical reflection so that you can see what that changes in terms of the graph and also the defining characteristics. Notice it does still have the parentheses cubed, so that means this has a parent function of y equals x cubed. And what it has are an a value of -2, an h value of 1, and then a k value of 0. Because you can kind of imagine a +0 on the outside. Okay, so the a value of -2 is going to end up doing two things. One, it's going to cause the graph to vertically reflect. That's because of the negative, but then it's also 2, so that will vertically stretch our graph by 2. And then the h value is going to cause the whole graph to shift to the right 1 unit. And then the graph is not going to move up or down because the k value didn't change from 0. All right, so as always when I'm graphing these, I start with the parent function, the function where I was just cubing x, and that function was centered at 0, 0. Then I'm going to do these transformations to my original parent function points. So I'm going to take my original x's and add 1 to each of them so that they will all move to the right 1 unit. And then I'm going to take my original y values and multiply each of them by -2, so that'll take all these cubes and stretch them and change their sign. So the x plus 1s, that's all of these. I just add 1 to every single one of those values, and it just causes the whole graph to shift to the right one. Then each of these y values, these cubes right here, I'm going to take each of those y values and just multiply them by -2. Hold on, I just want to use a different color here to make it clear. These are the transformed points. Okay, and so I take all these, multiply by -2, so the negative y values become positive, and they're also 2 times bigger than they used to. So that's a reflection and a stretch all in one. Okay, so when I plot this graph, so these are all my new ordered pairs right here. Notice how they're centered around HK. And now we'll go ahead and plot them. So I have a point at -1, -6, or -1, +16. 11, I'll just call it here. We're gonna have to fudge the graph a little bit so I can fit it on here. I'll just label the point so there's no confusion. Then I have a point at 0, 2, 1, 0, 2, -2, and then 3, -16. We'll just kind of put it down there and label it. So I have a graph that's now centered at 1, 0, so it's shifted to the right 1 unit. It's also very elongated because of that vertical stretch. It is now also decreasing over the entire x-axis. It's going down as x values move right. So that's what happens when you have a negative a value on a cubic function, is that this function is going to decrease the entire time over the entire domain. So -infinity to infinity. And the domain for this, that's all real numbers. The range is also all real numbers. They always are for cubics. What else? It's decreasing the whole time. We already mentioned that. It has a point of symmetry at 1, 0. That's the HK for this graph. I can see the y-intercept on the graph because it was one of the points in my table is 0, 2. But I could also find that by plugging 0 into the equation. So it was -2 times x minus 1 squared, or cubed, not squared. Gosh, dang it. Or -2 times 0 minus 1 cubed, which is -2 times -1, which is 2. So you can find it that way. The x-intercept is right there in my graph because this function only moved right one, it never moved away from the x-axis. So the x-intercept also happens to be the point of symmetry as well. And yeah, so that's our second graph, and it's defining characteristics. Okay, so now I want us to take a look at going the other way. What if I'm given the graph of my equation and then I'm being asked to write, given the graph for my function, and then I'm being asked to write the equation? So what you have to do is notice it's that squiggly S shape. So this has the shape of the parent cubic function. And so that's what tells us we want to use a HK form for a cubic. This is going to be the template we use because of the shape that this graph has. We can also look at the graph and notice the point of symmetry, which is going to tell you the coordinates for your h and k. So I have a h coordinate of 1 and a k coordinate of -4. So that's h and that's k. So really what I know is y equals a, x minus 1 cubed, and then -4. I'm 2/3 of the way done with my equation. I just need to solve for a. So that's what the other point helps us do, because I can use that other point as a temporary x and y. So this is a point at 0, -6. That's an x coordinate and a y coordinate on the graph. What that means is that when I plug in 0 for x in the equation, I should end up getting a -6 for y. So I just do that and see what a would have to be to make that true. So I solve this equation for a. So you got to do what's in the parentheses first, then you got to do the exponent. Then I'm going to add 4 to the other side, and then divide by -1. So in this case, the a value would have to be 2. Makes sense that it's positive because the graph is increasing. So I'm going to write my equation as y equals 2 times the quantity x minus 1 cubed, and then -4. It's a good idea to test it on Desmos to see if it gives the same graph. Maybe you could plug other points in to test and see if they work, although this one's kind of hard to get exact points. Looks like there's one right here. But you could, let's see, that's at 2, -2. If you want to see if your equation works, you could plug 2 into this equation and see if the y value ends up being -2. Maybe I'll just try that really quick. So I get 2 times 1 cubed, that's 2 minus 4. So yeah, so it works. So that's a way you can check your equation if you don't have access to Desmos. So there is an example of writing an equation. So that'll conclude this video lesson. What I want you to do is make sure you complete your note guide. And then we also have the handout to work on that you got in class for 3.1, Unit 3, Skill 1. So make sure that the note guide is completed and your practice handout is completed when I see you on Monday. Have a great weekend.